All right, hello everyone. So, last time we saw exactly what are first order homogeneous differential equations. In these equations, the derivative of y with respect to x is going to be a function of y over x. It's going to be a function of y over x, okay? And so, we saw that given that we cannot separate the variables in the equation as is, and if you see that it is indeed homogeneous, and we have a test for that, I'll just come to that in a bit. So what we should do is use the substitution v equals y by x. Okay, then we could express the derivative of y like this: v plus x dv by dx. You could either you could choose to derive this every time you do such problems, or you could memorize this portion. Either way, if we do this, if it is indeed a first order homogeneous differential equation, we make this substitution, we will definitely get a separable differential equation. We can solve for that separable differential equation. Well, hopefully, it's not like you can always take the antiderivative, so sometimes it's just not possible. But given that we can take the antiderivative on this side especially, so that one definitely we can. So then we'd get a relation between v and x, and we just need to back substitute. V was equal to y by x, so you just need to plug that in to then get a relationship between y and x, which is exactly what we want. And lastly, we discussed what is really the test for being a first order homogeneous equation. Sometimes it's not really that obvious. Often it is, so just sometimes it's not. So what do we do? What do we do at that time? For that, we said that, okay, so if our derivative is indeed a function of y over x, okay, so if suppose say our derivative expression is just some function of x and y, if that has to be a function of y by x also, okay, then if we were to substitute tx and ty, and really the reason behind doing these substitutions is because it's a function, it should be a function of the ratio of y and x. Okay, so if you multiply both of these by the same factor, you shouldn't be changing the function. The function shouldn't be changing. That's exactly what this this condition tells us. Is if we substitute tx instead of x here and ty instead of y here, we'll see that nothing changes. It we still get the same function on this right hand side, which is the derivative expression. Okay, so and to be honest, if you already suspect that some differential equation is homogeneous, okay, and you just want to test it to make sure. If the equation is not given in this form, you don't really need to forcefully write it as dy by dx equals some function of x and y. Not you don't have to forcefully keep this isolated on the left hand side. All you need to do is make this substitution, and at the end, what you should see is that the differential equation is unchanged. That's really all that matters. All right. So enough with me blabbering about the theory which we did in the last video. Let's move on to some problems. That's basically the purpose of this video. Let's move on to some problems. So the first one we have here, I'll start off simple, but this should do a good illustration of exactly showing the usefulness of this method. So what we have is y prime, the derivative of y, is equal to y plus x divided by x. All right. This compared to a lot of differential equations, even separable ones that we have done, this looks very simple. It looks really simple compared to a lot of things that we have done. However, it's still not separable. Okay, you can try to separate as much as you want. And really, what was our principle for separable equations? You could state it in a few ways. Many books state it in different ways. Suppose say, one you could say is you should have some function of y multiplied by dy equaling another function of x multiplied by dx. You should be able to bring the differential equation in this form. Okay, you could just spin it around a bit. You can just change this a bit. You could also say that the derivative with respect to x. Okay, so suppose they divide both sides by dx here. So and bring everything else to the other side. Basically, what you'd get is g of x divided by f of y, but 1 over f of y is still just some function of x. So this is another popular way of saying whether an equation is separable or not. Is your derivative with respect to x has to be some function of only y multiplied by some function of only x. You should be able to express your derivative in this form. This one I think is the clearest here. Is you know is the derivative of y some function of f multiplied by some function of x? Okay, and we could try some things. We could say it's y plus x multiplied by 1 over x, and even no matter how much we manipulate this or otherwise, you could add, subtract, divide a lot of things on both sides. It really wouldn't matter. The thing is, y prime is equal to this, and you can clearly see that this is a function of solely x. Okay, so that requirement was met, but this is not a function of solely y. This has both x and y in it. That's a major problem. That's why this is not separable. This is not separable. However, what we see here is if we just eyeball this problem, this should appear familiar what we did in the last video and all. So let's try to manipulate this a bit. So we have y prime equals y plus x divided by x. Let's just separate this fraction a bit. So we have y by x plus x by x is basically 1, and so this is basically homogeneous, a first order homogeneous equation. Why? Because your derivative of y is solely a function of y by x. Or if you make the substitution if you make the substitution v equals y by x, if you call this v, then your derivative y with respect to x is solely a function of v. It's v plus 1. It's v plus 1, and that is exactly why this is a first order homogeneous equation. So we can apply our this substitution to solve this problem. All right, and one more thing. Did mention that I'd talk more about this. So can we use this test? Can we use this test here? Well, of course, you can actually use this test anywhere. Okay, it's just that when it's really apparent that it's for a first order homogeneous equation, you don't exactly need to, unless your professor really wants you to rigorously prove that it's a homogeneous equation. You don't really have to use the test. But if we just wanna if you just want to do it rigorously, or if we even if we're uncertain, we could actually use the substitutions. So suppose say y prime equals, so it's y plus x divided by x. What I'm gonna do is, instead of y, everywhere I see a y, I'm gonna put ty. Okay, and everywhere I see an x, I'm gonna put a tx. So here I have tx instead of x. Here I have tx instead of x. And we see that all the the t's cancel out in both the numerator and denominator. So we have y plus x divided by x. And this is exactly what we needed. We needed this derivative expression to be unchanged even after this substitution. All right. So that rigorously proves that this is indeed a first order homogeneous equation. But anyways, either way, we know the fact that it's a homogeneous equation. Now definitely comes the most important part, is solving this equation. For that, what we saw, we could rework this every time, but we just saw this in the last video. So I'm kind of tended to just use this here. So we know that if we make the substitution v equals y by x, our derivative of y with respect to x is gonna be equal to v plus x multiplied by dv by dx, right? So let's put that in there. Let's put that in there. So on the right side, as we showed, we have v plus 1. On the left side, it's y prime, which is basically, as we saw, v plus x dv by dx. Okay, this is gonna be equal to v plus 1. So if we subtract v from both sides, we get x dv by dx is gonna be equal to 1, right? Yeah, so the v's cancel. Okay, so now things have become pretty simple. We can clearly see that it's separable. We proved that it has to be separable given that it's a first order homogeneous equation. Now let's multiply by x dx and divide by x. Okay, and yeah, it's just a 1 there. We don't need to do anything with that. So we have dv equals, actually we could even just say that dv by dx is 1 by x. Okay, our very old method of taking an antiderivatives. Okay, the simplest method to solve differential equations. So if the derivative of v with respect to x is 1 by x, well, what is v? It's the integral of 1 by x, respect to x. So if that's the case, we'll get natural log of absolute value of x plus some constant here. Okay, so now what do we see? Well, we can do a couple of things. We can do a couple of things. One thing is we should actually revert our substitution, right? So what was v? It was basically y by x. It was basically y by x. Okay, and that's and this is mandatory because we need a relation between x and y. That was, these were the variables in our original problem. That's why we cannot just leave v hanging there. So yeah, y by x is gonna be equal to c plus, natural log of absolute value of x. We have seen this already. Use the log rule to kind of like put a constant there, like, you could say it's natural log of absolute value of k, plus c could be, some natural log of some constant k, right? And then you can say it's the same as natural log of k multiplied by absolute value of x. So you could do that. And now finally we could multiply both sides by x, and we should have our solution. So lo and behold, y has to be equal to x multiplied by natural log of k multiplied by absolute value of x. Voila, we have our solution. We have our solution. Now, as and I really wanted to illustrate this fact is sometimes even if you have a very simple looking differential equation, first order differential equation, it may not be separable. Okay? It may not be separable, and it turns out a lot of times that these are in fact homogeneous, and that's why this substitution is so important. Okay, so important. We have two more problems. Let's go to the second one. So the second one, the next one is and all of this is equal to zero. All of this is equal to zero. So what do you do here? Well, there's really, and this is the thing that this is one of the things that I'm trying to convey in this video, is that people solve these equations in a lot of ways, especially, getting to, the differential equation involving v and x. From the original differential equation to this, people really, there's quite a lot of variation with how people go about this, whether they are rigorous and test for this, whether they don't do that, and even the way they substitute it. Okay, so let me show you something. One thing is, as I said, if it's obvious to you that it's gonna be okay, actually, first thing we should check it's separable or not. And to be honest, you can try it and it's really not. All right, so with that aside, if it's obvious to you that it's homogeneous, okay, and there's a couple of ways to think about this. One is, you can divide both, all sides by, actually, what should you divide by, and how can I detect that this is homogeneous? Okay, just by, eyeballing it. The thing is, every term you take here, if you expand all of this out, okay, that excluding the differentials, okay, I'm not going to count them in. So all of them have a total power of 3. Suppose that this is 2x squared y. So basically x squared y. See here, total power of 3. Okay. This is going to be negative x y squared. But anyways, x y squared, again, x to the power of 1 y squared. Again, a total power of 3. Same with here, it's y cubed. And same with all of these, x squared multiplied by, basically x cubed here, x squared y here. All of these have a total power of 3. And this is really a dead giveaway that this is gonna be homogeneous. Okay, so that's really how I eyeball these equations are, and most of the time it really works. I don't have to rigorously test for it. But if it's not obvious, and or if it's, if your professor demands that you rigorously prove that it's homogeneous before going into solving this, you could do that. Actually, before that, as I said, the way you make the substitute, suppose say I choose to do this by intuition. Okay, so I know that this is homogeneous. How would I make the substitution? Even that, there's some variation between people, but although that really doesn't matter much. One thing you could do is, you divide both sides by x cubed. Basically, x to the, power, the total power, x to the total power, basically. So you can divide both sides by that. Okay, so if we do that, what do we see? We have, this x squared goes away. We have 2 multiplied by y by x. Okay, I'll just expand it and also divide at the same time. The negative y by x whole squared. Basically y squared by x squared. So that's y by x whole squared, plus y by x cubed. And actually all of this is multiplied by dx. Okay, and with the dy's, this x squared goes out. Okay, so we have 2x by x is 2, and it's yeah. So let's see. We have actually I'll put a plus here, so it's negative 2, negative 2, negative 2 plus you basically have y by x here, so it's plus y by x, plus y by x. So multiplied by dy is going to be equal to 0. Now this is pretty obvious. If you make the substitution v equals y by x, that things would work out. Okay, now that is one way you could do the substitution. A lot of people also you know try to go another way, although it really doesn't matter, you get the same thing. So you could also, if v equals y by x, if v equals y by x, we saw that y obviously has to be equal to v multiplied by x. So if it's obvious to you that this is homogeneous, you could also just in this equation plug vx instead of y. Okay, here. So I'll just illustrate that again, as I've been saying a countless number of times. It really doesn't matter what you choose. So what we had is y in front, so it's vx. Okay, so we had a y here, so we put a vx there. So basically everywhere you see a y, you put a vx. So 2x squared minus x into vx. Okay, so yeah, 2x squared minus x into vx, basically vx squared. Okay, and I think it was plus y squared, right? Yeah, plus y squared. Yeah, okay, plus y squared. Then you have a dx, and you have, okay, so yeah, I think I got it. So you have plus y squared, basically it's v squared x squared. Okay, so and this is multiplied by dx, this is multiplied by dx. Now and then you have you subtract, let's see, x squared 2x, and then you have a minus y, so you are gonna put a minus bx there. And all of this is equal to 0. Actually, yeah, you have a dy here, and now it's very obvious that you have a common factor of x cubed on on this side. You can factor on an x cubed and you can divide that by both sides, and you'd get the same thing. You'd really, all of this, no matter how you really make the substitution and approach this, as long as you're sure that this is a homogeneous equation, you're really gonna get the same equation. Okay, so referring to this one that we did. Okay, it's gonna be, let's see, 2, okay, so it's gonna be let's see, 2v. So y by x is basically v, so every time we see that, we're gonna replace that by v minus v squared plus v cubed dx. Okay, and then v minus 2, basically. V minus 2 dy. Okay, and this is gonna be equal to 0. This is gonna be equal to 0. We would actually need to isolate dy by dx. Okay, so if we do that, suppose, say, if you bring dx to that side and divide, and okay, so what you're gonna get is dy by dx. I'm just gonna do some algebra quickly. So I'm basically taking it to that side. Okay, I'm taking it to that side. It's basically gonna be negated. Okay, and then I'm gonna divide by dx and divide by v by 2. So sorry, v minus 2. So basically what we're gonna have is negative v. So this thing is basically negated. So negative v cubed plus v squared, and then you have minus 2v, right? And this is basically divided by v minus 2. So this is what you're gonna get. Now we make, now since we have dy by dx, and we need dy by dx here. Okay, so now since we have dy by dx, we're gonna make the substitution. Okay, dy by dx, as we saw, is gonna be v plus x multiplied by dv by dx. Okay, and this is gonna be equal to all of this stuff, So negative v cubed plus v squared minus 2v divided by v minus 2. Okay, now one thing, if we subtract v from both sides, I think something interesting is gonna happen. Okay, so if we do that here, if we subtract v here, what we're gonna get here is, you can see that this portion right here is actually a multiple of this. It's just this thing multiplied by v. So you can actually bring out a v here. So what you'd have is negative v cubed v minus 2. If you divide this by this, what you would basically have is a v, because this thing is v multiplied by v minus 2. So if you divide this, what you're gonna basically have is plus v, then have a minus v, and it's very obvious these two cancel. Okay, so now I think it's pretty simple. So basically what you're gonna have, I'll actually neatly write this again. So you have x multiplied by dv by dx is gonna be equal to negative v cubed divided by v minus 2. All that we need to do is separate the variables. Okay, so if we do that, um, on this side, on the left side, what we're gonna get is, let's see, okay, so you're gonna get 2 minus v. I just actually, multiplied by the negative here, divided by v cubed, and this is multiplied by dv. But I'd like to simplify this a bit before integrating, so I can write this as, it was 2 by v cubed. So basically, I'm gonna write that as, 2v to the power minus 3. Okay, minus v, right? Yeah, minus v. So basically, you can write that as minus v to the power minus 2 multiplied by dv, and this is going to be equal to, if I divide by x and multiplied by dx. One thing is, in these equations, the right side is always going to be the same. It's going to be, x multi, oh sorry, 1 by x multiplied by dx. That's one way you could kind of like relieve yourself whether you're going in the right track or not. Okay, so if you don't get that on the right side, things are probably going wrong. Okay, so now if you take the integral on both sides here, since the variable is separated, on the left side, what we are going to have is a v to the power minus 3 raised to the power by 1, and then you also divide by negative 2. So what we're going to have is negative v to the power minus 2, and here raised to the power by 1, so you have negative 1 here, and then you divide by negative 1, so you have plus v to the power minus 1, and it's going to equal on the right side, as you saw, it's going to be natural log of absolute value of x and plus some constant. But we can write it as natural log of some constant k multiplied by the absolute value of x. Moving on, now what do we need to do? Since we got the relation between v and x, all that we need to do is reverse our substitution. So v was equal to y by x, right? Y by x. So v to the power minus 2, that's going to be the reciprocal of this, which is x by y squared. So this is negative x by y whole squared. It's going to be x squared by y squared. Similar thing here, it's going to be x by y. Okay, and it's going to be equal to natural log of k multiplied by absolute value of x. All right, now we do have our solution. This is a a valid solution to the differential equation. Just to beautify this a bit, we can multiply both sides by y squared. Okay, so what we're gonna have is negative x squared plus xy is gonna equal y squared natural log of k multiplied by absolute value of x. Okay, well, this is more or less the solution. We can, if we just want to bring everything to one side. Okay, if you do that, what you're gonna have is x squared minus xy plus y squared natural log of k multiplied by absolute value of x, and it's gonna be equal to 0. Voila, we have our solution. This is basically our solution. All right, and one thing I might have not mentioned before in this video, but one thing that we really need to confirm to make sure of, and it's also kind of relieving to see that it's true here, is that this is a first order differential equation. It needs to have one arbitrary constant. It's the general solution. It's not some particular solution that we are deriving from some initial boundary conditions. So since that is the case, it's a general solution. There has to be one arbitrary constant, which here is the k. Okay, if we don't have any arbitrary constants, we definitely made a mistake somewhere. Probably in the integration phase, we didn't add any arbitrary constant. That's something that we can be relieved about. So this was all the problems that I wanted to show in this video. So see you next time, and study smart.